This video we're going to talk about the conservation of linear momentum. This comes from the fact that the third law of Newton says that every force has an equal but opposite reaction. So if we have a wall and there's a person and the person pushes on the wall with a certain force, the wall is going to push back with the same force but in the opposite reaction. So if we combine this with what we learned about momentum in Newton's real second law, we hear that if we ignore friction, the net force felt by the wall is pretty much equal to the force of the person exerting on it. And since net force is equal to the change of momentum over time, we can say that the change of momentum that the wall feels because of the force of the person divided by time is going to equal to the opposite change of momentum that the person feels caused by the force of the wall and the person divided by time. And since time is the same, we can ignore it, and then we get the equation that the change of momentum of the wall is equal to the negative change of momentum of the person. And since the momentum lost by one, being the person, because it's negative for this case, is equal to the momentum gained of the other, which is in this case the wall, we can say that the total momentum of the system, meaning if we add the momentum of the wall and we add the momentum of the person at the beginning and then add the momentum at the end, the total change will be zero, because however much one gains is equal to the other lost. So it's really, really similar to the conservation of mechanical energy, the one that says that the change of kinetic energy is equal to the negative change in potential energy. But if you remember, this only works if the total work done by the non-conservative forces is zero. This whole conservation of momentum is always true for closed systems. Now, what does a closed system mean? Well, a closed system pretty much means that when you look at everyone, for example, if we imagine a classroom and we look at all the people inside the classroom, that is our closed system. Right? The total mechanical energy in this system will not change. So if we were all, for example, standing still, and then we all started running around, because when we were all standing still, our total momentum was zero. When we start running around and we add the momentum of everything inside the classroom, it's zero. To get up off the chair, you have to push your chair back, meaning your chair is going to gain momentum in the opposite direction that you're gaining. So in the end, everything cancels out. You push one person moves in one direction, the person pushing moves in the opposite direction, and in the end, the total momentum still ends up zero because we all started off not moving. Now, that doesn't mean that the total momentum always equals zero. Again, that simply means that the net change in momentum is zero. So we could have started off with momentum. Maybe someone came running into the classroom and came with some momentum, or we started looking at it when we were all running around. But if we looked at the total momentum of the system, it would not change. If we start off with 20 kilograms meters per second, then we're going to end with 20 kilograms meters per second. The only exception if there's a force acting outside the system onto the system. So something very dramatic would be if we had like a meteor come in and hit the classroom, then there will be a change of momentum because we have an outside force acting on the system. So let's look at this example of how to use conservation of mechanical energy. We start off with, we have a 2.35 kilogram cart that is rolling across a frictionless, now the key word here is also it's rolling across a frictionless horizontal track towards a 1.5 kilogram car that is held initially at rest. The carts are loaded with a strong magnet that causes them to attract one another. Thus, the speed of each cart is increased. So they're accelerating towards each other. At a certain instant before the cart collides, the first car's velocity is 4.5 meters per second. The second car's velocity is negative 1.9 meters per second. This is a one-dimensional problem. And alright, so basically we have two objects. They're being forced, they're both experiencing a force caused by their magnets, which is equal but opposite, pushing them together. So let's look at our givens. So we know the mass of cart 1, we know the initial velocity, well, we don't know there's the initial velocity, but we know that there is an initial velocity because the problem says they're rolling. We don't know the acceleration, we don't know the V final. We do know the V final, it's positive 4.5. For car 2, they give us the mass. They give us the initial velocity 0 because it said it was initially at rest. And we don't know the acceleration, and we do know the final velocity is negative 1.9 meters per second. Alright, for part A, they want us to find the total momentum after the moment of the collision, which they give us the information for. So the total momentum, since we're only looking at two objects, is the momentum of object 1 plus the momentum of object 2. The momentum of the first object, it's just its mass, which is 2.3, times its velocity, which is positive 4.5, which tells us that its momentum right before the collision is positive 10.35 kilograms meters per second. The momentum for the second car is just the same thing, its mass times its velocity, which gives us negative 2.85 kilograms meters per second. And when we add those two together, our total momentum is positive 7.5 kilograms meters per second. That's our answer for part A. For part B, they actually want us to find the velocity of that first car that was rolling. The way we solve that is using the law of conservation of mechanical energy. The law of conservation of mechanical energy says that the total change of momentum of a closed system is 0, which means the total momentum of the cars added together at the end equals the total momentum of the cars at the beginning. And we found that out from the last problem that that's going to equal positive 7.5 kilograms meters per second. So that means when we add the initial momentum of part 1 plus the initial momentum of the object 2, it's going to equal 7.5. The total momentum of object 1 we don't know because we know the mass, but we don't know the velocity. But we do know the total momentum of object 2 because it started from rest, so the total momentum of object 2 is 0. So then we can set it up to the equation that 7.5 is equal to 2.3 times our initial velocity of object 1 plus 0. And then when we do the math, we find out that the initial velocity of object 1 was 3.26 meters per second. And that's our answer. That's the initial velocity of the first object that was rolling. Alright, for this problem we have a two-stage rocket. And it's in space and it's moving at a constant velocity at 400,900 meters per second. These two stages are separated by an explosion, making the top 1,200 kilogram upper stage move at 5,700 meters per second in the same direction as before. And the explosion, what is the velocity and magnitude and direction of the 2,400 kilogram lower stage after the explosion? So if we look at it, we have a two-stage rocket, each with its own individual mass, and it's moving forward at 4,900 meters per second. There's an explosion that separates it. The top part keeps moving forward, but this time at a speed of 5,700 meters per second, meaning it's sped up. And the other piece, we do not know how fast it's moving. So we're kind of wondering, did it slow down or did it start moving in the opposite direction? There's your explosion. The explosion there exerted a force of equal but opposite direction for both these. The explosion allowed the 1,200 kilogram to speed up, and it's either going to cause the 1,200 kilogram to slow down or actually move in the opposite direction. The only way to find out is to actually try to calculate it. So the solution is to first find out what VF is. We start off by what we did before. We know that the total change in momentum needs to be 0, meaning the total final momentum and the total initial momentum have to be the same. So we don't have enough information to find the total momentum at the end, but we can find what the total momentum at the beginning is. The total momentum at the beginning is the mass of the total object, which is the 2,400 and 1,200 kilogram, times the velocity it is moving at. So when we figure this out, we find the total momentum of the rocket before the explosion. We find out that the total momentum of the rocket is 1.764 times 10 to the 7th kilogram meters per second. So we set our initial equal to our final, and from there we can start calculating our final momentum. So that means our final momentum, the total final momentum, is equal to the final momentum of the 2,400 kilogram piece plus the final momentum of the 1,200 kilogram piece. And the final momentum of the 1200 kilogram piece is its mass times its velocity, which we know, which gives us positive 6.84 times 10 to the 6th. And the final momentum of the 2400 kilograms we don't know because we don't have the V final. But we can plug them back into our equation and solve for our V final. And we calculate that our V final is actually 4,500 meters per second positive. It's still positive, which means the second part is still moving in the same direction as before. It just slowed down a little bit. And that's our complete answer. For the last problem of the video, we have a situation where there's an accident and there's a plate being dropped. It says, by accident, a large plate is dropped and breaks into 3 pieces. The 3 pieces fly apart parallel to the floor, and as the plate falls, its momentum has only a vertical component. No component parallel to the floor. After the collision, the components of the total momentum parallel to the floor must remain 0, since the net external force acting on the plate has no components parallel to the floor. Using data shown in the drawing, find the masses of piece 1 and 2. So basically what they're saying is, this is a top view. This is the plate after it hits the ground, as if you're looking down on it, and it like scatters parallel to the ground. So when the plate is falling, if we look at the side view, the plate is falling straight down, which means that its total momentum in the left-right direction is 0, because the only force acting on it is gravity, so it's not moving left or right. So, and then when it hits the ground, the plate moves parallel to the ground. So this is what we see. So this is why the net momentum has to be 0, because the plate was only moving down. It wasn't moving parallel to the ground. So the net momentum in relationship to the ground is 0. So in order to set this up, we have to do things in a 2-dimension, because we have the plate moving in both the x and y component with respect to the ground. So a good thing to do would be to break up its velocity into its different components. So for the mass 1, we find that the velocity in the x is 0, its velocity in the y is 3.07 negative. We do the same thing with the mass 2, and we find out that the velocity in the x is 1.27, the velocity in the y is also 1.27, and then we find the velocity in the x and the velocity in the y of plate 1. Now that we have that information, we can actually try solving it. So since the total momentum initial in release when we're talking about to the ground is 0, the total final momentum to the ground is 0. And since momentum is a vector, we can also say that the net momentum in the x must be 0 and the net momentum in the y must be 0 for the total momentum to be 0. So once we separate things into its x and y components, we can kind of find it easier to deal with. So the net momentum in the x is the mass 1 times the velocity 1 in the x plus mass 2 times the velocity of that piece of the plate with the x plus mass 3 times the velocity of that piece to the x. And then we do the same thing for the y components, except we look at only the velocity in the y direction. And we get our 2 equations. Once we start plugging in some of our knowns, we know that they're both the x, the total in the x and the total in the y have to be equal to 0. And since we know the velocity in the x, we get negative 1.27 times whatever mass 1 is, plus 1.27 times whatever mass 2 is, plus 0. Oh, kind of got a little head. So then when we solve this, because the reason M3 is 0 is because it's only moving straight in the y direction, has no x component. Then when we solve this, we find out that the mass of the piece 1 has to equal the mass of piece 2 in order for the x components to cancel out. So this is going to be really important and help us out when we try to figure out the next part, because when we try to figure out the y component, we get 2.72 times m1 plus 1.27 times m2, and this is again by plugging in the velocities in the y direction, minus 3.99. The reason we know it's 3.99 is because we both know that the mass of piece 3 is 1.3 and the velocity is negative 3.07, so when we multiply them together we get negative 3.99. And since mass 1 and mass 2 are the same value, we can actually add those components and we get 3.99m, I'm not going to say m1 or m2 because they're the same mass, minus 3.99 is equal to 0. That means m is equal to 1 kilogram, which is the same as mass 1 and mass 2. So the mass of plate 1 and plate 2 is both 1 kilogram.